Yes, sir.
Mm.
I mean, he lives in Tottori. I mean,
Yeah, right,
so
right. Got a chance to meet him? No, not yet.
yes, sir. Yes, sir. We have met him. I mean, like we have. I mean, already met her quite a few times.
Okay, okay, good. Yeah, we just sat with Shubham yesterday for some work. So, Shubham Sarkar, I mean, of your batch.
He's not from our batch, sir.
Shubham
Hmm?
Bose, sir, actually. Shubham
Shubham,
Bose.
yeah.
Shubham Bose. Oh,
Oh,
Shubham.
Shubham
I am
Bose is different.
confusing.
Yeah.
Sir,
Shubham Bose
Ritobroto Dobe is
probably
also my batchmate from presidency. Ritobroto Dobe.
Dobe, yeah.
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 That's okay. I understand. Shubham Bose is in ONGC না এখন না শান্তনু where is he
Uh,
ও সুপ্রিয়র কাছে কাজ করেছিল তো সেই শুভম তো
No. He is talking
না
about
না
Shubham
না
from
না
Jadavpur University.
No, sir, Shubham from presidency.
Oh,
no no
acha,
no
acha.
no there was a শুভম বোস একটু বেটে করে তাই
আচ্ছা
তো
আমাদের ব্যাচে তো তো
তোমাদের
আমাদের
ব্যাচের
ক্লাসে
I can
হ্যাঁ
remember yes শুভম বোস very reserved sort of a boy.
ইয়েস স্যার
Hmm. No, I'm confused. There are so many Shubhams and so many Sayans in geology that you it's quite a long time. ভুলেই যাচ্ছে আর কি। শুভম সরকার বিদিশাদের ব্যাচ শুভম সরকার is your junior Dipto?
ইয়েস স্যার ইজ আর জুনিয়র
They are your junior. Okay, fine. Anyway, I think we can start and let's not talk about all these things.
I
We
think,
can
I
talk
think,
it in
I
a
think,
later
I think
forum.
people will chip in. In the meantime, please introduce our speaker, Arun.
Okay. Sir, should we start or wait for
Yeah,
some
sure.
time?
I think
Okay. Okay.
yeah.
So, good afternoon, all, and welcome to the SGT SGI monthly e-lecture series. Today we have with us Dr. Sivaji Lahiri. Is the speaker who is going to talk about mechanical compaction mechanism of sediments. So, before jumping into the talk, let me formally introduce Dr. Sivaji Lahiri. Dr. Lahiri did his PhD from IIT Kharagpur with Professor Manish Mamtani sir. Then after he moved to RWTS Aachen University in Germany, where he did his postdoc with Professor Janus Urai. And soon after he joined Simfar Dhanbad as a scientist. At such a young age, he has already published more than 10 research papers, and that itself highlights his research excellence. With this short introduction, now I hand over the platform to Sivaji Lahiri. Over to you, Sivaji.
Okay, thanks a lot. Can you see my slides?
Yes.
Is it visible? Okay.
Yes.
Okay, thanks a lot. Good afternoon, everyone. Myself, Dr. Sivaji Lahiri. Now, at this moment, I am working as a scientist at CSIR Central Institute of Mining and Fuel Research, Dhanbad. So today in this presentation, I am going to talk on mechanical compaction mechanisms in the input sediments of Sumatra subduction complex, insight from microstructural analysis. Now, first, what is mechanical compaction? Now, here you can see there is a typical sedimentary basin. Now, within this sedimentary basin, over time, layers after layers, sediments will get deposited. Now, the layer of the sediment, which was deposited earlier, over time, it will become heavier, denser, and less in porosity because of the deposition of overlying strata. Now, this particular phenomena is known as mechanical compaction. Now, here in this research work, we aim to understand the deformation mechanism associated with mechanical compaction within sedimentary basin. To do it, first we collected samples from IODP. Actually, in 2016, IODP, that is International Deep Sea Drilling Program, they performed drilling within Indian Ocean, just beneath Sumatra subduction zone. Now we collected samples from them. Now here you can see there is a typical porosity versus depth plot corresponding to these samples. Interestingly, we can observe at the shallow depth from seafloor to 30 meter, there is a rapid or sharp reduction in porosity. However, at greater depth from 30 meter to 1300 meter, we can observe there is a reduction in porosity with smaller gradient. Now, here in this research work, we aim to understand the deformation mechanism associated with reduction in porosity in this fashion in the sedimentary basin. So first, we collected samples from IODP. This is the typical sample. You can observe that we have received from IODP. Thereafter, we tried to polish the sample using broad iron milling technique. Now, utilizing this technique, we can prepare very smooth, polished sample surfaces. So if we utilize this technique, we can prepare sample surfaces with undulation less than 5 nanometer. So very smooth sample surfaces. After that, we tried to capture images of the sample surfaces using scanning electron microscopy. So here you can see this is the typical secondary electron images of this particular sample, and this is the backscattered electron image corresponding to the same sample of the same surface area. Now in the next few minutes, I am going to show you some interesting microstructures corresponding to these samples. To do it, I have considered 3 representative samples. Sample SN1 from 1 meter depth, sample SN6 from 28 meter depth, and sample SN33 from 1300 meter depth. So let's try to see how the microstructure of these samples are changing with increasing depth. Now this is the sample SN1 from 1 meter depth. You can see there are lots of different types of pore spaces within this sample. Now among all of these different types of pore spaces, I would like to mention 2 important types of pore spaces. First, silt adjacent larger pore. So here you can see there is a typical silt particle, and adjacent to that there is a very big pore. This is the first one, or the first type. And the second type is typical clay domain surrounding larger pore. So here you can see there is a very big pore, and the surrounding that there are lots of clay particles. Now I am specifically mentioning these 2 types of pores among all of them because these 2 types of pores are going to play a very critical role with increasing depth to reduce porosity in these samples. Nevertheless, if we try to look at the particle contacts, here in this sample, we dominantly observe 3 different types of particle contacts. That is edge to face, then edge to edge, as well as face to face. So all of these 3 types of particle contacts are very abundant within this particular sample. Now this is the sample SN6 from 28 meter depth. Now, interestingly, within this sample, dominantly we observe this kind of face-to-face particle contacts. However, edge-to-edge and edge-to-face particle contacts are very rare here in this sample. Nevertheless, if we try to look at the pore structure, here in this sample, we dominantly observe this kind of silt adjacent larger pores. However, this type of clay domain surrounding larger pores are very rare in this sample. Now, based on this observation, we can conclude collapse of clay domain surrounding larger pores caused rapid or sharp reduction in porosity at the shallow depth. Now coming to the deformation mechanism, in the sample SN1, we dominantly observe 3 different types of particle contacts, that is edge to face, as well as face to face particle contacts. However, in the sample SN6, we dominantly observe this kind of face to face particle contacts. Now based on this observation, we can conclude rotation appears to be the dominant deformation mechanism at the shallow depth from seafloor to 30 meter depth. Now, let's try to concentrate on the samples of 30 meter to 1300 meter depth. Now, here in this depth range, we observe small reduction in porosity, or maybe I can say reduction in porosity with smaller gradient. Now, this is the sample SN6 from 28 meter depth. You have already observed in the earlier slide. And this is the sample SN33 from 1300 meter depth. You can see how the microstructure of this sample has got changed with increasing depth. Now, in the sample SN6, we dominantly observe this kind of silt adjacent larger pores. However, in the sample SN33, this kind of silt adjacent larger pores are almost missing. Now, based on this observation, we can conclude that reduction in number of silt adjacent larger pores caused reduction in porosity from 30 meter to 1300 meter depth. Now, coming to the deformation mechanism, here in this depth range, we observed very interesting deformation mechanism. So let's try to have a look at them. Here in this particular microstructure, you can see that there is a silt particle. Adjacent to that, there is a silt adjacent larger pore. On the top of that, you can observe there is a clay particle, and the clay particle actually got fractured. Now again, you observe there is a silt adjacent larger pore. On the top of that, there is a clay particle, and this clay particle actually got bent because of the compaction strength. Same thing, you can observe here that there is a silt particle, there is a silt adjacent larger pore, and the top of that, there is a clay particle, and this clay particle actually got bent. But here you can observe, of course, there is a silt adjacent larger pore. There are, clay aggregate on the top, or the bent clay aggregate on the top. And among that clay aggregate, one clay particle actually got fractured. Now, based on this observation, we can conclude that bending and fracturing of the clay particle appears to be the dominant deformation mechanism for reduction in porosity from 30 meter to 1300 meter depth. Now, I would like to concentrate on this particular microstructure. So this is a very interesting microstructure. Here you can see there is a quartz silt particle, there is another quartz silt particle, and in between them, we can observe there are some small clay particles. On the top of that, you observe there is a aggregate of clay particle, and this aggregate of clay particle actually got bent. Now, interestingly, if we try to look at the number of small clay particles present within this small space in between two quartz silt particles, you can see there are only small 4 clay particles present. You see, you observe here. If one clay particle fractured, ultimately what is happening? 2 small clay particles are getting developed. If 2 clay particles gets fractured, then 4 small clay particles will get developed. Now try to look at here within this particular space, almost 4 small clay particles present. So based on this observation, we can conclude that this particular microstructure is representing a kind of paleo silt adjacent larger pore. The pore space within the 2 silt particle actually got reduced because of the bending and fracturing of the clay particle. So based on this observation, it appears that within the depth range of 30 meter to 1300 meter, bending and fracturing appears to be the dominant deformation mechanism to have reduced in porosity in these sample sets. So at the shallow depth from seafloor to 30 meter, you observe rotation as the dominant deformation mechanism. However, at greater depth from 30 meter to 1300 meter, we observe bending and fracturing as the dominant deformation mechanism. So there is a transition in deformation mechanism occurring at around 30 meter depth. So the question arises, why there is a transition in deformation mechanism occurring at around 30 meter depth? Answer to this question is actually space problem. Initially at the shallow depth from seafloor to 30 meter, samples had lots of pore or vacant spaces within it. So particles can easily afford rotation. However, at greater depth, From 30 meter to 1300 meter, samples did not have enough pore or vacant spaces surrounding them. So particles could not afford rotation. So particles got deformed by bending and subsequently fracturing. I think you can also do a very small experiment using the pen which is there in your hand. You try to rotate your pen, you will find that you need actually more larger vacant spaces surrounding it. But when you are trying to, bend the pen, you need actually smaller space, which is happening here in this particular, samples. Now, similar kind of thing we also observe in our day-to-day life. So this is a typical image that I have tried to take from one of the YouTube videos. So here you can see there is a typical Japanese morning train and the train compartment is fully packed. There are still a few passengers are trying to go inside the train compartment. Now just try to see there are two persons with a white shirt. How they are standing? They have just got bent. So if you ask these two persons to rotate at this condition, they cannot rotate because they do not have sufficient pore or vacant spaces surrounding them. Now here you can see there is a lady standing inside the train compartment and the train compartment is less crowded. So if you ask this lady to rotate at this condition, she can easily rotate because she's having lots of pore or vacant spaces surrounding her. So sometimes whatever we observe in the micro scale, we also observe in our macro day-to-day life, and probably that's the beauty of the nature. So thank you. This is a small presentation.
Thank you, Sivaji. Such a wonderful talk. Yeah. And now the platform is open for discussion.
Okay. Yeah. Thank you, Sivaji, for a very crispy talk. So, just I want to know, it's a very beautiful one, and it's very, you can relate the things with the natural things, day-to-day life things. I have a little question, a little query about the things, not a question. Do you know that the type of clay mineral that you have has a role to play? Or any sort of clay mineral? There are different clay minerals like elite, smectite, galenite, like this, right?
Yeah.
So, do you think that this different type of clay mineral has got any role to play there? This is just a curiosity.
Yeah, I think that there will be role. Here in this particular sample set, so most of the clay are actually elite. That is what being reported by other studies. They did XRD and other thing. But according to your question or answer to your question, of course, I think that there will be effect, because if we consider different clay minerals, I think all of these clay minerals are having actually different strength. So if you consider smectite group of clay, generally smectite group of clays are very soft compared to elite or other group of clay, because in smectite generally we get OH group within the interlayer or the within the TOT layers. So smectite is as much maybe I can say weak clay. So if the clays are weak, then of course we can compress it in a much better way. So what will happen? The porosity will be reduced in a much more faster rate. But what I understand is that the deformation mechanism, I think, will not have any play or anything with respect to the type of clay. The deformation mechanism will remain same, but what can happen? I think the porosity reduction can be faster if we change the type of clay.
Okay. Another thing that you showed different geometry of pore space related to your adjacent to sealed as well as clay, I think.
Yeah.
What is the reason for that? Just a curiosity again.
Yeah, we tried to actually first, initially in our work, we tried to separate different types of pores. Initially, actually, we tried to look at pores considering, around 7 to 8 different types. There is a very well-known classification of pores within shell, which is being provided by, I think there is one author, I cannot remember the name. So he actually suggested in 8 different ways, actually we can try to classify pores that present within any mud rock or within any shell. So initially we tried to deal with all of these 8 different types of pores. But later on, we realized that the drastic change in the porosity is actually happening because of these 2 types of pores. One is the clay domain surrounding pores. Clay domain surrounding pores means, maybe I can try to share here. Clay domain surrounding pore. Clay domain surrounding pore means here you can see there is a very big pore just surrounding to that. Lots of clay particles are present. You cannot see any silt particle or the typical silt particle. But here you can see there is a very big pore. Just adjacent to that, there is a very big silt particle. So we actually realized that these 2 types of pores are playing very critical role, because when we are trying to look at the samples of around 28 MBSF depth or the 28 meter depth, we are observing that this sample does not have too much this kind of larger clay domain surrounding pores. Then we realize that maybe these clay domain surrounding pores are playing very critical role to have reduction in porosity at the shallow depth.
This is not unnatural with increasing the effective load, because as you go deeper, effective load is increasing. This is quite natural, isn't it?
Yeah.
So I'm just trying to understand what is. This is only due to the weight of this column.
Yeah, exactly. That is what mechanical compaction. The porosity is reducing because of the effective stress. Effective stress means that is because of the weight, maybe you can say. Yeah.
So you don't have any chemical reactions for changing the porosity in your study?
There are lots of studies. People have reported that because of the chemical reaction, porosity can be changed. But here in the sample sets, we do not have any evidence of as such, alteration or maybe recrystallization and all of these things. That's why this sample set provides us a very unique opportunity to understand the mechanical compaction or the deformation mechanism related to mechanical compaction. So that's why we have restricted our study only for mechanical compaction.
Okay, Sivaji, I think there are other people waiting for you to respond.
Yeah, I think Sayan Maiti has raised his hand. Yeah, okay. Please go ahead.
Hi, Sivaji there. How are you?
Yeah, fine. How are you?
I'm fine also. Nice presentation. I have just one query. That how do you think the proportion of silt and clay, like the proportion of clay and the sand particles or the quartz particles, will change the mechanics or change the dynamics of the change in microstructures?
Yeah, it has actually lots of effect. It's a very important, very interesting question, and lots of people did lots of experiments regarding it. Okay, so what I would like to say is that if we try to look at any microstructure like this, okay, we are having broadly 2 components. One is the silt particles. So silt particles are larger and stronger particles, because most of the time they will be quartz, maybe you can say feldspar, and also calcite and other particles. And surrounding, we are having clay particles. So clay particles are always very soft. Okay. Now the interesting point that I would like to mention, when this kind of compaction process is actually happening, the line of force always tries to pass through the silt particles, because the silt particles are stronger in nature. Just for an example, you can think, the building you are just, sitting at this moment. Try to look at your building. What is happening?
Hello.
Hello.
Yeah. Just can
So
please
this is a very interesting thing. If you just try to look at your building, what is there in your building? What are the components? You are having pillars.
Pillars and the bricks and the cementing material.
Exactly. So how there are pillars? How these pillars are being made? There are iron rod. Then there is cement. So these pillars are the strongest part or the strongest component within your building. So why these pillars are there? Because these pillars are passing most of the line of force of your building, most of the weight of your building. Okay. And you are roaming around within the building. This where actually you are roaming around, that is actually nothing but your stress shadow zone. That's why you are stable. And that's why your building is not collapsing. Same thing happening in case of your rock. So if coming to your question, if there are lots of silt particles, then what will happen? Most of the line of force will pass through those silt particles. So what will happen? Just adjacent to that silt particle, all of the silt adjacent pore will remain as it is. So they will not collapse. So if you increase the percentage of silt particle, automatically your porosity in the sample will increase. And there will be less compaction within the material. And if you increase the clay particle, so the way I can say, if you look at your building, if you reduce the number of your pillar, what will happen? Your building will collapse. Why it will collapse? Because you are reducing the stronger particle from the system. So in case of clay, or in case of shell, if you leave or if you reduce the number of silt particle, what will happen? It will be more compressed. Your porosity will be reduced in a much more faster way.
Yeah, but is not that the case that in that case where the silt particles are more in number, like the quartz particles, they will they will collide or something like that, and
Yeah. That is what I am saying. When they will be in contact, most of the line of force or most of the weight, maybe you can say, okay, most of the line of force will pass through those silt particles. Are you getting my point?
Yeah.
Most of the line of force will pass through this silt particle. Now, adjacent to that silt particle, there will be stress shadow zone. So within this stress, you see, these silt adjacent larger pores are nothing but these are actually the pores which is there within the stress shadow zone. Are you getting my point? For example, here you see there is a silt particle adjacent to that. There is a very big pore. Why there is a very big pore? Because the pores exist because there is a stress shadow zone.
Pressure shadow kind of thing.
Yeah, same thing, pressure shadow zone or stress shadow zone, whatever you say.
Yeah.
Okay. Yeah, so if we increase the number of silt particle, then what will happen? Your stress shadow zone within the system will increase. So more number of silt adjacent pore will remain within your sample. So as a result, what will happen? Your porosity will be more. Yeah.
Okay. Thank you.
Okay, I think Nilanjana sir has one question. I think Nilanjana sir, please go ahead.
Am I audible?
Yeah, sir, please.
Shivaji, it was a nice presentation, and that you spoke from your heart is very evident the way you spoke. So I really liked it. Now, these sediments are oceanic sediments?
Yes, sir.
Okay, so they are close to some subduction zones?
Yeah, they're close to subduction zone, but we did not get too much deformation within these sediments. Maybe I can say approximately 350 kilometers away from the subduction zone, almost.
Oh, so the forces operating within the subduction, they are not playing within these sediments.
No, sir. Yeah. So that's a very because if the faulting and other processes are operating within these sediments, then we would have not studied this kind of. We would have not studied this kind of microstructural analysis, because there will be an effect of the subduction zone stresses.
Right.
It is not there. Sir.
Right.
Yeah.
It's not there. So it's free from those microfracturing and microcracks and all those things.
Yes, sir.
And these are elite. Are these orthogenic elites or smectite turned elites?
So these are actually, sir, orthogenic elites. So we did not study that. There are a few researchers who tried to understand that aspect. So from the past studies, I come to know that these are specifically elite, but these are not because of the transformation of smectite to elite. These are orthogenic elite.
So how my query is like how do you get elites under a system within water which is not so proficient with potassium? I mean, are these elites brought from some place or they are orthogenic? I mean, this is what I wanted to know, because that would give a variation in the sediment structure.
Yes, sir.
And in the compaction, because whatever you're talking is below diagenesis, right?
Yes, sir.
There's no scope for any thermal or anything of that sort.
No, sir. That is actually, sir, the above diagenesis level. Maybe I can say diagenesis is a broader term. What I understand, although I am not a sedimentologist, I am a structural geologist. My focus was to understand the deformation mechanism. But what I understand is that diagenesis is a much broader term, so it encapsulates all of these aspects. and mechanical compaction is within them. But if I consider the crystallization or maybe dissolution, precipitation, and all of these things, so we did not find any evidence
No,
of
no,
it.
that is beyond the question because it doesn't go to that level at all. I mean,
Yes, sir.
it's just mechanical loading which has
Only
given.
thing is that. Yes, sir.
Did you try to do any EBSD sort of thing on these to find out whether there are any microstructural domains which are showing heterogeneous behaviors?
Sir, EBSD, sir, I had a target to do EBSD, but the problem is that, sir, doing EBSD of clay minerals is very difficult. That is what I
Difficult.
understand. So once actually I tried, I found that there are only a few papers. People have tried to do that. So I think, sir, there is a very well-known professor. I think his name was Wink. Yeah. So he did lots of this kind of microstructural studies in US. So I found actually a few papers written by him. Later on, sir, for one sample, actually I tried to do that. I was actually trying to understand how the EBSD, anisotropy factor and other things are changing with increasing depth. But I found it's very difficult, and we were not getting any reliable data. So then we left our target or research related to that.
These are cohesive things, no? These are cohesive things. I mean, they don't disintegrate under microscope. You are doing same.
Yes, sir. I was doing the same. SEM.
Interesting,
Yes,
very interesting. Nice work.
okay, thanks.
Thank you.
Yes, thanks.
Anyone else?
Hello?
I think, yeah. Yes, please go ahead.
Hello?
Hello.
No, I don't have any further questions.
Okay.
So
Okay.
maybe somebody else.
Okay, sir. Thank you. Yeah. I think I have one question, Sivaji. Your samples are from close to a subduction zone, right?
I think there is some
Yeah.
problem with the.
Yeah, Sivaji. Hello.
Yeah, Arun,
Yeah.
please.
Yes. I think your samples are from that Andaman subduction,
Yeah.
close to that Andaman subduction system. That means we should expect a lot of seismogenic stuff, like seismogenic related compaction in your sample. So, is there any evidence for seismogenic related compaction?
Yeah. Yeah, the point is that where actually this drilling is being done, the position is almost 350 kilometers away from the subduction zone. So it is much far from the subduction zone. So people actually did not get too much evidence of seismogenic activities within this sedimentary unit. So we did not find, even while actually we are trying to do the microstructural analysis, we did not find any any of such evidences. So this is just that's why actually we are able to do or able to understand the process of mechanical compaction. Okay, because if there is any disturbances, then we would not have able to do this analysis for understanding mechanical compaction. Yeah.
Okay, so your sample is some kind of like ideal sample to test these
Yeah,
mechanical loading.
it is not ideal because in natural case it is very difficult to get
Yes.
ideal sample.
Yes.
Yeah, so the point is that I'm trying to mention in the earlier studies, if you see, most of the people did lots of experiments related to it. And there are a group of studies where people have tried to do or tried to say that rotation is the dominant deformation mechanism for mechanical compaction. There are lots of studies, lots of experimental studies.
Okay.
But while actually we have tried to look at the microstructure of the natural samples, we observe something different. We observe that there is rotation at the shallow depth, but at greater depth we observe bending and fracturing as the dominant deformation mechanism. So that's actually our finding, which is contrast with respect to what people did. Maybe you can say the typical experimental studies. So yeah. So that is the kind of finding of this particular research work.
Okay.
Yeah.
I have another doubt. In your sample, you have quartz grains and also clay. Okay.
Yeah.
So if we change the sorting of those quartz grains, then the porosity also change. then
Yeah.
how the sorting will affect your porosity depth if you have different degree of sorting?
Yeah, so shorting has a very important or interesting relation with porosity. So the point is that if we increase shorting, porosity will increase. If we decrease shorting, porosity will decrease.
Yeah.
Okay, because if we decrease shorting, what will happen? There will be lots of small particles, and also there will be lots of larger particles. So what will happen? All of these small particles will take place within the pore space of the larger particle. So as a result, overall porosity of the sample will reduce. Now coming to our research work, you see this is a thick sedimentary section of almost, you can say, 100 and 1300 meter thick. So what actually we did, we tried to contact with IRDP, then we tried to collect the samples which are having almost similar mineralogical composition. That is the first thing, because just now, Shayan has already asked a very important question, that if there is changes in the mineralogical composition, then of course the compaction process will be affected. So we have tried to consider a few things. First, all the samples should have the similar, almost similar. We cannot say that exactly same because this is a natural sample. So all of these samples are having almost similar mineralogical composition. That is the first thing. Second, all of these samples are having almost similar shorting. They don't have any, any such, maybe I can say, too much changes in geochemical aspect. So all of these different, points that we have tried to consider while we are trying to, finding out, or where we are trying to collect these samples from IITP for our study. Yeah.
Okay, thank you. Any more questions from Santul sir? Has already done. Okay. Any questions from Anupam sir? Do you have any question?
Sorry, actually, I was involved in another meeting. Right now, it is finished. So I'm very sorry that I missed the lecture by Sivaji. And I really wanted to listen to him, but unfortunately, I missed it because I tried my best. But as you know, when a meeting starts, you don't have any control of ending it.
Yes.
So it just finished and I logged in, but by that time, I think his presentation is over. And anyway,
no, Arun told me that Shivaji presentation should be small. Arun told me very fast.
That is when your topic was very interesting. Yeah. Your topic was very interesting. I think we'll have a YouTube link later. Yes. I can watch. Yes. Anyway, I'll enjoy the discussion. That's all. Thank you.
Okay, sir. Any more questions from? I think we have no more questions. Ramon sir, Anupam sir, should we conclude the session or we should wait for some time? I think.
Yeah, Dr. Ramon, I think because I am just a late intruder, almost post-kinematic magmatic intrusion. So like, excuse me for this particular this particular lecture. Just I have not listened to the presentation. I have a general question to Sivaji. Is that when you, I mean, just I saw your topic that you were showing the fate of the sediments that are going inside the deep subduction zone and the compaction things from your microstructural study. So my question is, what is the implication of this of the dehydration of these sediments on the weighting of the mantle wedge? I mean, you see, there is a ongoing debate of deep serpentinization in the mantle wedge and the exhumation of serpentinites along the subduction channel and its emplacement. There are a lot of debates on that, whether they are going to mark paleo subduction, or whether this was also operative in the Proterozoic or on the Precambrian period, especially in marking the paleo subduction zones. So do you have you, because you have worked possibly on the Andaman subduction zone, so do you have any idea of the dehydration of the sediments leading to hydration and serpentinization of the mantle above?
Sir, I actually, sir, did not work in that aspect. Actually, I tried to understand the deformation mechanism within the sediment or related to mechanical compaction. I did not work in that aspect. But one point I would like to, maybe I can say, based on my observation on this sample set, that I think, sir, probably there are lots of waters are going within the subduction zone because there are different processes actually. Now, one of the point maybe I would like to mention. I think we are all familiar with there was a 2004 mega earthquake occurred in Andaman subduction zone. Probably one of the biggest earthquake occurred in the last 100 years. Yeah. So.
Yeah, not really in last 100 years because 1960 Chile earthquake was the largest, which is 9.5.
Or maybe in the last 30 to 40 years because its
second
Richter scale was
largest.
9.2 or something like that. Yeah, it's a very big earthquake. Yeah. So one of the point maybe, sir, I would like to mention that in most of the studies that I have observed is in earlier people used to say that all of this big earthquake and large earthquake were occurring because of the deep-seated fault. But in the recent time, people have started to say that all of these big earthquakes are occurring because of the shallow depth fault. In fact, there was another earthquake that was occurring in Tohoku, Japan, in 2001, which causes that Fukushima disaster. The people observed kind of similar thing. There is a very shallow depth, earthquake that occurred, there. Now there was a paper which is written by Bean et al. In 2009. That paper actually got published in Science. It's a very well-known paper. I have tried to read, where actually they have tried to mention that that in case of Sumatra subduction zone, there is a layer which is very well known as HNF layer. There's high amplitude negative polarity layer. So they identified that there is a layer which is highly enriched in fluid content, and they have interpreted that this entire layer is actually going down during the subduction process, and that water within it is actually causing the earthquake and other thing. So based on this study, maybe I can say that of course lots of waters are going there within the subduction zone, but serpentinization and other process, sir, I have never worked on it.
No, that is right. But in fact, serpentinization, petrological aspect is different. But even just as a matter of discussion, because I am not referring to your presentation, I have not listened to it. In general, that also this kind of dehydration phenomenon in the sediments on which you are studying, that also has some potential implication for the depth of the earthquake. Because if you see the earthquake profile in a subduction zone, then there are some shallow earthquakes and there are some intermediate to deep earthquakes. So in between there is a zone where there is not much of earthquake focus, generally recorded. So if there is a possibility that is the area where much of dehydration of sediment is taking place, and if waterborne minerals, hydrated minerals like say serpentine or talc or these kind of things happen to form, then they actually make the part weak, no doubt.
Yes, sir.
But at the same time, they are not seismogenic.
Yes, sir.
They actually change the friction to stable friction rather than stick-slip friction. That is that is well known from experiments and as well as
yes, sir. The stick-slip process actually causes big earthquake.
RDS faults and other places. So that can also have the depth distribution of earthquake can have an implication on this. These are the implication of the depth distribution of earthquake. That is possible. Anyway, it was just a casual question. So I think if anyone else has any specific question from your presentation, then I can also learn something from them. Otherwise, as Arun was suggesting, we can make an end to the session. I'm done.
Yes, Sivaji. I think I have one doubt. That 2004 earthquake that is in the Andaman zone, and that earthquake should have some impact on those sediments. That core samples. Why we didn't observe any sort of seismogenic signature in those core sediments?
Yeah, actually, there is a shallow depth earthquake that occurred in Sumatra subduction zone. I have just mentioned that people earlier used to believe that there was deep-seated earthquake which used to develop this kind of tsunami and other things, but they observed actually completely different aspect. But coming to your question, that as I have mentioned, that drilling was done almost 350 kilometers away from the subduction zone, so it is quite far away. And if you look at the offset of the Sumatra subduction zone earthquake that happened in 2004, it was just beneath the subduction zone. So it is almost more than 350 kilometers away, where actually this faulting and other process actually happened. Okay, so actually, one point maybe I would like to say, this IODP people, okay, these IODP people actually had target to collect samples from where actually this earthquake occurred. Okay, that was actually their objective. But when actually they started the drilling and other processes, okay, then this Indonesia government and all other government actually did lots of complaint related to it. Then they shifted their ship and they come to the international sea and they drilled there. They tried to collect the samples which are actually getting subducted after maybe a million of years. Okay, so they did not get it. Okay, so that's why in these samples, they did not find as such evidence of any fracturing or faulting or any kind of thing. Yeah.
Maybe the intensity is very low because 300 kilometer, that is not sufficient enough to cause any liquefaction or
In
subsediment
general, in
formation.
sedimentary rock, the effect will be much lower if you try to understand, if you see, because if there is hard rock, then of course the effect will be much larger. You will get much more fracture and faults and other things.
No,
But
I'm
if there
talking
is
about
sedimentary rock, where there is lots of clay and lots of shell, lots of clays, then what will happen, these clay particles are much more smaller size. So it is having actually much more surface area, these clay particles. So what will happen ultimately, it can absorb much more shock compared to maybe other particles. So as a result, always in a sedimentary rock, we always get much more less effect of earthquake and fracturing compared to probably other hard rock. So that's the reason probably maybe you can see even after 350 kilometers away from it, they did not find as such evidence of earthquake and faulting.
I think
Yeah.
we have no more queries. I think we should conclude the session. Thank you, Sivaji. Thank you.
Yeah.
Such a nice
Thanks a lot.
presentation. Yeah.
Yes.
And
Thanks a
all,
lot, sir.
have a nice weekend. Okay. Bye
Yeah.
bye.